going to transform these into a complex problem. That is, I'm going to be working with what we call the complex analysis. So what we are going to be doing now is the method or the approach we are going to be taking is on complex analysis, how we evaluate integral using complex analysis. So consider C. This is a key point or keyhole singular point. That is, whenever you have a curve, look at what I'm going to do. I will let f of z to be equal to, I have s raised to the power of n minus 1 over 1 plus x. So I'll let f of z to be also equal to z raised to the power of n minus 1 over 1 plus z. So we'll find the singular point, or what we call pole. So don't forget, suppose we want to integrate, suppose we want to obtain integral of f of z on this curve, on this curve that I have here, or on this closed curve or contour. Integral of f of z on this curve, don't forget, by residue theorem, this will be equal to 2 pi I, then I have sum of residue on residue at singular points. So that is what I'm going to be using here. So f of z is z raised to the power of n minus 1 all over 1 plus z. I want to integrate on this c of f of z. Don't forget it to be equal to, this is purely based on complex analysis, residue theorem, 2 pi I sum of residue. So what am I going to do? What is the singular point here? Of course, you will equate the denominator, 1 plus z, equate it to 0, z equal minus 1. And I can write this z equal minus 1, that's a singular point. In fact, a singular point, a simple pole rather. It's a simple pole because it just occurs once. I can write this from the elementary. This is equal to e raised to the power of I pi. E raised to the power of I pi from the elementary. If you convert minus 1, if you write minus 1 in the exponential form of a complex number, this is equal to e raised to the power of I pi. So I will now find the residue of f of z at z equal -1. Residue of f of z at z equal -1. Don't forget, this will be equal to limit as z goes to e raised to the power of I pi, because e raised to the power of I pi is same as -1, as I've showed you here. This is from elementary. Don't forget, e raised to the power I theta is cos theta plus I sine theta. So when theta is pi, if you put it here, you will get 1 minus 1 plus 0, and that's -1. This is from the elementary aspect of complex number. So this is limit as z goes to e raised to the power I pi. Then I have z plus 1, because it will be z minus z naught, which is z plus 1 f of z. So this is equal to limit as z goes to e raised to the power of I pi. Then I have z plus 1 multiplied by f of z. F of z is z raised to the power of n minus 1 over 1 plus z. 1 plus z cancel 1 plus z, so you will be left with z goes, limit as z goes to e raised to the power I pi of z raised to the power of n minus 1, and this will be equal to e raised to the power of I pi, then n minus 1, as you can see on the board. So that is the residue. So that means that if I want to integrate, and that's the only singular point we have in this question. So if I want to integrate f of z on this closed curve, on this thing, I have integral of f of z to be equal to, which is integral from on c of z raised to the power of n minus 1 over 1 plus z is equal to 2 pi I multiplied by this. So I have 2 pi I multiplied by e raised to the power of I pi n minus 1. That is what I am going to have. That is what I am going to have. Now, what will happen next? But from this curve, look at it. This is a keyhole neighborhood. I have a singular point. I what's it called? I avoided the point 0. I avoided the point 0. That is what I have here. Look at what happened. I have a curve C, and then I avoided the point 0. I take 0 here as a singular point, so I avoided this. I want the function to be analytic throughout C. So look at what happened. Integral on this curve, integral of f of z on this small circle, I call it radius r, small letter r, and this big circle is of radius r, capital letter R. So it's equal to, I have from here a to b, this circle, this integral of f of z on this curve is equal to integral from a to b. As you can see, integral of ab f of z plus integral. Then I have b, d, e, f, g throughout the curve. Then I have b, d, e, f, g of f of z, plus then I have again g to h plus integral of g h of f of z. Then lastly ha comes to this integral of h a f of z. So in reality, from what I have drawn here, that's how I obtain this integral on this curve C. On this curve C is equal to, as you can see, this is a straight line A to B, right? Then I have a whole circle from B, D, E, F, G. That's why I wrote integral from B, D, E, F, G. Then I also have GH, another line, another straight line, parallel to the x-axis or parallel to the real axis. I have GH. Then lastly again another circle HA, as you can see on the board. So now let me just write this well. This will be equal to integral of C of f of z dz is equal to integral. Now AB, before I do this next one, don't forget, whenever you want to compute in complex analysis, z is always represented as e raised to power I theta. You will let z to be equal to r e raised to power I theta. That's the exponential of a complex number. So whenever you see z, you can represent it as this. Now differentiate the z will be equal to, differentiate with respect to theta will be equal to ir e raised to power I theta with theta. So what the radius is, it will be r. If the radius is capital R, you have capital R. If the radius is small r, you have small r, as you can see here. So look at what we are going to do next from here. So the first thing is this will become integral of C of f of z is equal to integral of AB. What is AB? AB is a straight line. The boundary is R to small letter r. So that is from R to R. And in fact, it is not a curve. It's just it's parallel to the real axis. So I can write f of z as s raised to the power of n minus 1 plus x dx. What has happened here That is for this first integral. What has happened here is that since I just have a straight line, so I can take just the real part of z or the imaginary part of z, because it's just a straight line, that's all. So if I take the real part of z, instead of writing r raised to power I, so the real part is just x, and besides, this x is just a dummy variable of the integral. You can see the boundary is bounded from this capital R to this small r, plus now I have a full circle B, D, E, F, G. That's a complete rotation. So that means the boundary will be from 0 to 2 pi. The boundary will be from 0 to 2 pi. Then what's f of z? F of z, I'm writing in exponential form. Don't forget the radius of this big circle is r. So I have r e raised to the power of I theta over 1 plus r e raised to the power of I theta multiplied by dz. dz is ir e raised to the power I theta to theta. So this is raised to the power of n minus 1. Don't forget f of z is z raised to the power of n minus 1. So this is just z r e raised to the power I theta, then raised to the power of n minus 1 over 1 plus z r raised to the power I theta multiplied by dz. dz is ir e raised to the power I theta to theta. So this is ir e raised to the power I theta the theta, as you can see what I have written, plus the third one as well. The third one is gh. Gh, that is from here to here. So this is integral from the capital R will be here, the small r will be here. Now this is also, this one will also be written as the real, like we won't write the complex form of this. But don't forget, the function has completed a revolution already. It has completed a circle. So this is what I'm going to write. I'm going to write s raised to the power of n minus 1, obviously. But I will multiply by e raised to the power I 2 pi. E raised to the power I 2 pi is 1. If you compute e raised to the power I 2 pi from the elementary, that's cos 2 pi plus I sine 2 pi. The answer will give you 1. So it does not really change anything. But the purpose here is just that why I'm putting e raised to the power I 2 pi is because so as for you to know that it has already completed a full circle, that it has rotated around and it has come back to this place. That is why I'm writing e raised to the power I 2 pi. Then this is raised to the power of n minus 1, then the s. And beside, e raised to the power I 2 pi is obviously 1. Then the last one plus integral. Then HA is also another circle here. It's also another circle. Of course, this one will now be from 2 pi to 0 of f of z. And f of z, of course, this one will be small letter r. R e raised to the power of I theta raised to the power of n minus 1 over 1 plus r e raised to the power I theta the theta. But the z is equal to multiplied by I r e raised to the power I theta the theta, as you can see on the board. So this is the next thing we are going to do. So let me tell you the plan here. The plan here is that I will take limit as r goes to infinity. You know, don't forget this is integral from 0 to infinity from the question. I have integral from 0 to infinity. So I'll take capital R to go to infinity. Then take this small r to go to 0. So that I will have something like integral from 0 to infinity. So I'll say as r goes to infinity, that's what we have, that's the first case. And number 2, and the small letter r goes to 0. as r tends to infinity and this small r goes to 0, what happens? What happens is that if you look at the second integral very well, if you look at the second and the fourth integral very well, they will cancel out. So before God and man, this one will go to 0 when r goes to infinity, and also I claim this one will also go to 0 as r goes to 0. This one is quite obvious because as r goes to 0, when by the time you put r to be 0 here, 0 divided by 1 will give me 0. Integral of a bounded or the definite integral of 0 is 0. Now in this case, look at r. I'm just going to consider r for you to see. This is r raised to the power of n minus 1 multiplied by another r all over just r here. So this is r raised to the power of n over r. But don't forget where we are coming from in this place. This n is less than 1. It's between 0 and 1. That's what we are going to have. This n is between 0 and 1. Don't forget, this is how we got to this place. You say gamma of p, gamma of 1 minus p is equal to pi over sine p pi. So you say p, where p is between 0 and 1. That is the case of gamma function, and this is what we evaluated, and we got this. So this p is representing n here. So n is between 0 and 1. So what my point is, the r at the denominator is greater than the r at the numerator. So I can write this as 1 over r raised to the power of 1 minus n. And as r goes to infinity, you have 1 over infinity, and that will give you 0. So that is why this and this goes to 0. So I'll be left with, so as r goes to infinity and this goes to infinity, the second and fourth integral goes to 0. So this and this will be out. So I'll be left, I'll be having integral of f of z to be equal to, now don't forget r has gone to infinity, then r, this other one has got, is now in 0. So I have integral from 0 to infinity now of s raised to the power of n minus 1 over 1 plus s raised to the power over 1 plus s ds. Then I have also this one plus integral from infinity to 0 of this one will be s raised to the power of n minus 1, then multiply by this one will become e raised to the power of I 2 pi n minus 1 over 1 plus s raised to the power of e raised to the power of I 2 pi ds. That's what you will be left with. This one and this have gone to 0. So the next thing that will happen now is swap the integral. You swap the integral, you'll be having, now what is the value for this? You've calculated this already. This is 2 pi I e raised to power. This is 2 pi I. The value of this one is 2 pi I e raised to power of I pi n minus 1 is equal to integral of from 0 to infinity of s raised to the power of n minus 1 over 1 plus s ds. Then, of course, I told you whenever you want to swap the integral, this negative, you just take the negative. This is minus integral from 0 to infinity of s raised to the power of n minus 1 e raised to power I 2 pi n minus 1 over 1 plus x e raised to power of I 2 pi ds. So this is the next thing I'm going to do now. Look at what I'm going to do. So from here, this is 2 pi I e raised to the power of I pi n minus 1 is equal to, this is integral from 0 to infinity of s raised to the power of n minus 1 over 1 plus s ds minus, now e raised to the power of I 2 pi n minus 1 is a constant. It will come out of the integral, so that I will have e raised to the power of I 2 pi n minus 1, then I will be left integral from 0 to infinity of s raised to the power of n minus 1 over 1 plus s. Now e raised to power I 2 pi obviously is equal to 1, I've told you before, so I just compute the values to it. This one will not necessarily be equal to 1 again. It depends on what n is before you know the value of this. So you leave this like this. For e raised to power I 2 pi is cos 2 pi plus I sin 2 pi. Cos 2 pi is 1. Sin 2 pi is 0. So this is 1. So I have 1 plus s ds. So the next thing that will happen will be 2 pi I e raised to the power of I pi n minus 1. What you will notice is integral from 0 to infinity of s n minus 1, integral from 0 to infinity of s n minus 1 factorized, so that you will have 1 minus e raised to the power of I 2 pi n minus 1 integral from 0 to infinity of s n minus 1 over 1 plus s ds. So that means to obtain the value, to obtain the answer, the variable side by 1 minus e raised to the power I 2 pi n minus 1. So this is equal to integral from 0 to infinity of s n minus 1 over 1 plus s is equal to 2 pi I e raised to the power of I pi n minus 1 over 1 minus e raised to the power of I pi I 2 pi of n minus 1. So at this junction, divide both numerator, maybe I should write it, divide both numerator and denominator, divide both numerator and denominator by e raised to the power of I pi n minus 1, divide of the right hand side, of the right hand side. So divide both numerator and denominator by e raised to the power of I pi n minus 1 of the right hand side. So this one will become integral from 0 to infinity of s raised to the power of n minus 1 over 1 plus s ds. Now by the time you divide this by e raised to the power I pi n minus 1, you will be left with 2 pi I all over. If you divide this one divided by e raised to the power of I pi n minus 1, you will be having e raised to the power of minus I pi n minus 1. Then I have minus this one as well. By the time you divide this one by e raised to the power of I pi n minus 1, this is what you are going to be having. You are going to be having e raised to the power of I pi n minus 1, as you can see. So the next thing to do is so we are almost getting to the end of this. The next thing to do is integral from 0 to infinity of s raised to the power of n minus 1 over 1 plus s ds is equal to 2 pi I over, this one is e raised to the power of minus I pi, I n pi, let me write it as n pi, then minus times minus will give me plus, so I have multiplied by another e raised to the power of I pi, then I have negative minus e raised to the power of I pi n multiplied by another one e raised to the power of minus I pi, just I pi. Yes, that's what I'm going to have. So this is equal to 2 pi I over e raised to the power of I pi, that is cos pi plus I sin pi. The answer is minus 1. So minus 1 multiplied by this will become minus e raised to the power of I n pi. Then e raised to the power of minus I pi is still the same. This one will give me cos pi minus I sin pi. The answer is still 1. So the answer is still minus 1. So minus times minus gives plus. So I have plus e raised to the power of I. This is minus I n pi, then this is I n pi. So this will become, bring out this pi, you'll be left with 2i. Then let me write this first. At the denominator, e raised to power I n pi minus e raised to power of minus I n pi. So you remember from the elementary that, of course, e raised to power I theta is cos theta plus I sin theta. This is from the elementary. E raised to power of minus I theta is cos theta minus I sin theta. Then if you subtract this from this, you will end up having sin theta to be equal to e raised to power I theta minus e raised to power minus I theta over 2i. So if you take 1 over sin theta, 1 over sin theta is equal to 2i all over e raised to power I theta minus e raised to power minus I theta. That is what you are going to have. This is very basic. This is complex number. So this is from complex number or from complex analysis. Now to round off this particular question, it follows that integral from 0 to infinity of s raised to the power of n minus 1 over 1 plus x ds must be equal to pi all over 1 over sine n pi. Why is this sine n pi? Don't forget this is I n pi. Whenever this is I theta, so when theta is n pi, you have sine n pi. So that at the end of the day, therefore, integral from 0 to infinity of s raised to the power of n minus 1 over 1 plus x ds is equal to pi over sine n pi. And that's all. So that is how we obtain this answer. So therefore, I told you before we are going to prove this later in the previous video, but now you can see that whenever you have beta of n and 1 minus n, which is equal to gamma of n, gamma of 1 minus n is equal to this. We've showed that before, and it's obviously equal to pi over sine n pi. Don't forget, 0 is less than n and is less than 1. Thank you very much.